We are live here on this lovely Wednesday evening, and we really have one main guest today. It is Steve Cook. Steve, remind us, what is your, I know you're with Hisense, what is your title?
National Manager, excuse me, bad timing. National Manager for Technical Operations Training. It's national, but I also really just North America. International sounds weird. But
okay, yeah, it sounded like you made that up as you were going along. So
I mean, I really,
he's like national, really not sure. No, international.
No, I guess it is international because I spent
universal,
half my time in Canada.
Intergalactic training manager.
I think is a bit more appropriate.
Yeah. And we also have our good friends Matt Bruner and Adam Mufich. So we're going to be talking through communicating systems now. This is one of these topics that, we can go into like oscilloscopes and all the details and all that stuff. We're going to touch on some things, some terms, but a lot of it is going to be a good opportunity for you guys to ask questions about communicating systems. We're going to talk about things that you should know as an installer, things you should know as a service tech, some different kind of protocol stuff from different manufacturers. But Steve has been around this space for a long time. I wanted to just kind of start, Steve, if you could just quickly introduce like the sort of things that you've taught on and a little bit about your background.
So in regards to this, to communicating equipment, I'd say the last 8 or so years of my career has been really focused on VRF equipment. And that all of that is very, very heavy emphasis on communication. But prior to that, I was in the field as a service tech working on this equipment. And I'm not going to say this is the most joyous, loving equipment. There's definitely some frustrations I have with a lot of the stuff. But it's a willingness to work on it. And that's kind of the epiphany moment I was sharing with Adam and Matthew earlier, that no one else around me was willing to work on this equipment. And it was getting out there in the field. So the kind of taking it by the horns and really running with it and kind of adapting it, getting used to it. It's not the easiest thing, but it does become, the more you work with it, the easier it is to understand.
And I think it's just worth mentioning, Matt's going to be asking most of the questions tonight, but I just right off the top want to mention that when we're talking about communicating systems, obviously, like Steve mentioned, VRF, VRV is kind of his world. We always have to throw in the VRV just for the Daikin people out there. But there's a lot of communicating equipment out there, both in the commercial side of things and in residential. And a lot of the principles apply in both places. But even in the world of like market refrigeration, where we do a lot of work, you have a lot of communications in that world as well. And essentially what we're talking about is equipment that uses control strategies that are not just on, off, 24-volt type of systems. As soon as you get kind of beyond that, you're generally talking about communicating controls. So with that, I'm going to turn it over to Matt to start asking the questions.
Yeah. So Steve, just from a high level view, how do these systems work and yeah, what are their purpose?
Really, the easiest way, I mean, these are all, like Bryan just mentioned, when you get into communication equipment systems, you're losing the 24-volt AC systems. You're kind of getting away from that. And really, the reason for that is really for the added complexity that's within the system, that's within the equipment. If you think about a 24-volt AC control thermostat, and you'll learn hopefully through this, at least this live stream that everyone watching, is when you get to a communicating machine system, we no longer have thermostats, we have controllers. So thermostat is what we use for a unitary non-communicating system. But you think of let's say a unitary ducted Goodman, Train, whatever it might be, system, York, whatever it might be. That 24-volt AC thermostat is essentially just a switch. It's a multi-switch. It can do a couple different functions, and each of those functions is carried on its own wire. So the most basic systems would be 5-wire. You'll have a wire. We all know this. The wire for heating, cooling, fan, all of that. So each of those, every time you energize one of those conductors, you will send a signal to to the piece of equipment to run in whatever mode that is. Now, if you think of a communicating system, there's a lot more things going on. So in order for the efficiencies to work or get the efficiencies, we might have inverter-driven equipment. And so in order for a compressor to speed up or slow down, they need to see what thermistors are doing. They need to see what the compressor is doing, the temperatures that are being throughout the system. So in order for that to take place, there has to have some sort of communication between the two in order for it to speed up or slow down. But these are all DC communicating systems. There's several different, there's several different protocols, you would say, and you consider a protocol as think of like a language. You have English, you have Chinese, you have Spanish. Each protocol, communication protocol, is its own language, and each brand will adopt its own protocol. I have not seen any brand use another same protocol that works with another one, and so that's kind of the language barrier.
And do you think that's a big part of why it's so difficult, or people feel so intimidated by getting into communicating systems and trying to understand, what's going on from a troubleshooting perspective?
I would say it can be, and because it's not something. The problem is, which we touched on it earlier, was the lack. I won't say the lack of information, but the information where it lives isn't the most useful for most technicians in the field. You can find that information in service manuals, but no one's going to have that with them. So this is where it is crucial to, if you have a communicating system that you work with, or if you sell a certain type, to really get in and understand that brand the best as you can. But each brand has their own carrying signal, which would be part of that protocol. And you think of when you think of a communicating system that's DC communication, think of two people speaking. So if I'm speaking English and you're speaking Chinese, we're not communicating. If Bryan and I are speaking English, we're communicating. And so these DC systems, they run on two wires. It's a sending and a receiving. So just like as if we were talking, and there will be a carrier signal, which that's the bit that varies from brand to brand. So Mitsubishi runs 29 volts. Daikin is, I believe, 16.5. Hisense runs 5 volts DC. So that's the actual live, wherever you check the signal. And that also, the definition of those terminals change from brand to brand too. But it'll be 2 points that you can measure from, like in Mitsubishi, it's M1, M2. Hisense, it's 1 and 2. I believe Daikin's F1, F2. Someone correct me if I'm wrong there.
I think it's just 1 and 2.
Okay, we'll go with that.
Yeah.
But those voltages are what really push the signal, but the communication is sent through essentially data packets, pulses. And so every time, let's say an outdoor unit wants to see what the temperature is of an indoor unit, it'll send a pulse out and it'll say, hey, I want to know your return temperature. And that indoor unit will return a signal telling the outdoor unit what that return temperature is. So that's why it's very crucial to make sure there's no addressing errors in the communication system. That's why we do have addressing, so that we know what we're talking to. If everything's addressed the same, you're going to have communication faults. And that's why it's also crucial to make sure, as far as working on it and knowing it, it's installed the best it can be. So using the right wire, using the right size wire, because all the knowledge in the world as far as how this equipment works, it is kind of pointless if it's not installed right. So if you might know what the voltage should be here and here, but if they ran the wrong wire, if they landed on the wrong terminals, that's not going to help you, because you're trying to find something that's just not there. So it all kind of goes down to proper installation. It's good for troubleshooting, but finding that stuff is very challenging sometimes. And I agree, it is very brand specific. Some brands make it easy, some brands make it challenging to find.
All right, I want to hop in here. Mike Cianfrocco. I always say Cianfrocco. I don't know if that's the right way to say it. I'm sure that's an incorrect pronunciation. Neil Comparetto says when you're saying Italian names, you should do this, and it helps you say it more correctly. So Cianfrocco. I don't know, but his question is, tell me why, or what he's asking for is, tell me why communicating systems. Why a communicating system versus a 24-volt system, like I'm a homeowner, sell it to me. So what are the actual benefits to the end user, and in as simplified terms as we can, of having communicating systems over 24 volts?
Really, that kind of ties to what I said a moment ago. So as we're trying to get higher efficiencies with our air conditioning equipment, and I know a lot of people, including myself, really just want the most basic stuff that just doesn't break. But with government regulations, with manufacturer regulations, there's a higher drive for more high efficient equipment. And to get to those efficiencies, we need to see more parts of the system. We need to see what's going on. Not just, when you look at a unitary system, the outdoor unit, a 24 volt AC control, the outdoor unit has no clue what's going on inside. And we all know this. I don't know how many times have we come to an indoor unit where the coil's frozen and you've got a filter that's completely stuck to the coil, and the coil is just a block of ice. That's clear. There's no communication. There's no communication there saying that my indoor unit is a block of ice. Let's keep running outside. It doesn't know. So in a communicating system, it would see these conditions. It would either back off. It would do what it needs to adjust accordingly. Or in the case that something's wrong, it could throw a fault. It could throw an alarm. But in these cases, when you look at, let's say, a mini split or VRF system, the outdoor unit has to communicate with the indoor unit in order to get to these efficiencies. So let's say we want to run the compressor faster, or we need to slow it down. We need to see what's going on inside the system. And a 24 volt AC control cannot do that for us.
Hey, Steve, let me ask you a question. I was just curious. I know you have a lot of experience in VRF in general. VRF technicians, communicating inverter technology in that. How easy is it if you're a technician working on, let's say, Mitsubishi or Daikin or something like that, to jump across the brand line and run service on another manufacturer's equipment?
Actually, I'm really glad you brought that up. So last year, or I guess earlier this year, well, it's not quite last year, at the symposium, Roman and I spoke about VRF equipment, and the whole emphasis on what we were talking about was to demystify what's going on, to kind of pull the curtains back. Because if you go to these trainings, if you go to Mitsubishi training, if you go to Daikin or LG, they'll all tell you what you learn there is only good here. How Daikin does their stuff is totally different. Runs on witchcraft and sorcery. We don't know what they're doing over there. But you kind of get this at the factory level. What you learn here only stays here, and that's really not the case. Communication protocols are different. So like Mitsubishi uses a Modbus communication protocol. Hisense uses Homebus. They all kind of, they're very similar, and those are kind of the languages talking about. So like Modbus is a language, Homebus is a language, and these are the things. They all operate in a very similar manner. So you're going to have a carrying signal. So that will change from brand to brand. So in the case of communication, you'll see 5 volts DC on Hisense. You'll see 16 on Daikin. You'll see 29 on Mitsubishi. Those will change. But as far as how they communicate and how they talk to each other, it's the exact same. They all send pulses in a binary signal to add. So you'll have a sending and receiving pulse. One component will send it to another, and they're all talking to each other. So it's the exact same. If you look at an inverter, Roman did a really good write-up earlier this year about inverters. And I don't know how many people have torn apart an outdoor unit and actually really looked at an inverter board and seen the terminals. It doesn't matter what brand you have. The terminals that go to inverter drive, the compressor, you'll have NP, typically you'll have UVW. Those are all the same. And you're going to see nearly the same readings on those from brand to brand. Like, that's not going to change. As far as inverter goes, you'll see, balanced 3-phase voltage to a fan or a compressor. So whatever that is doesn't really matter. That's irrelevant.
Do they run like similar like protection strategies, and they're looking for similar things? Like, I'm guessing, okay, everyone sort of needs to protect a compressor the same way, right? Like,
there are some logics that are different. Most of them are, in the grand scheme of things, we're all doing the same thing. It's not like we're making, this company's air conditioning, this company's making snow cones. We're all doing the same thing. We all have the same goal, is to produce comfort, heating, or cooling. And so there's not too many ways that you can do that, really. I mean, you can get a little different. Mitsubishi's got a little different with the two-pipe, but they're not changing any laws of thermodynamics. It's just an extension of their outdoor unit is moved inside.
Yeah. It's just like, we don't know what it's telling the other parts. Maybe that's kind of what freaks us out, I think.
And it's
like, if I put my probes on there, I don't know what it's saying, and I want
so if you were to put probes on it, there's a slide in the presentation that shows a meter with some sine waves on it, and those are nearly impossible to read on a meter. And this is pretty much what we're looking at here. So this is an oscilloscope here, and what we're reading here is a Daikin comm bus. And so my eyes aren't the best, but it looks like that's better. Yeah. Okay. So we got about 16 volt sine wave, and you can see each of these are pulses. And so these are sending and receiving. You're never going to be able to see these with a meter. The only way you're going to see this is with an oscilloscope. And the only people that have oscilloscopes are really geeky people like Roman.
He brings it up a lot. He brings up how his oscilloscope is better than my oscilloscope like every day.
Whose is bigger?
I don't have one.
Right.
I mean, I just rely on Roman to do this stuff for all.
He carries it around. He's like, look at the size of my oscilloscope. I'm like, I know, you win.
He carries it. Whatever. He still uses the gold chain for it.
He does it. Yeah.
Good for him. But you'll never see this on a system. If you take your meter, you'll never see this, and you'll never pick it up. You will pick up the voltage signal, which, let's just say Mitsubishi. If you're reading from M1, M2 on a communicating system for VRF, City Multi, you'll pick up 29 volts. Now you're not going to see what's going on, because there could be, when you think of a VRF system, there's going to be thousands of communications going on at any given moment. Wow. Unless everything's off, which in a VRF system, highly unlikely. But even if it's off, it's your sampling temperature. Something's happening somewhere. Anytime anything's happening in that system, you're going to get a pulse. And that pulse will go back to a control. It'll be a communication signal saying, hey, this is what we've got going on. Okay. And it's happening all over the place. So catching those pulses, I would say, is not relevant. It's more so knowing what we're trying to communicate with. And so this is what I was talking about. This is where it's crucial to have the proper size wire, which that varies from brand to brand. The correct wire, which would be stranded, shielded wire, not solid. And the solid, I'll talk on that for just a moment. Anytime you pull wire, Romex, you pull it with bits of rage. You're not really gentle with it, and so it usually bends. And when it bends, just think about if you're taking a coat hanger. If you bend that coat hanger a couple times, eventually it will break. And so each one of those bends, you're making these micro fractures in that solid wire, that solid core wire. And when those fractures are there, you could be communicating. You could see that DC voltage. You could see 29 volt DC on one end to the other. But with those fractures in that solid wire, that could interrupt those pulses to the whatever sending and receiving signal. So it may not communicate well. You may not get a communication fault. You might eventually, but not initially.
Yeah. So what's interesting is the unit that I have in my house, it actually calls for solid core wire. So, and a lot of Brian's like, okay, well, maybe I'm wrong, but a lot of them allow you to use old, a previously run wire. So can you speak to that a little bit?
I can safely say none of the install literature that Mitsubishi has, as of a year ago, that I was messing with, ever called out solid core wire. And so we had to train this, but when it got down to it, because you get some of these contractors would say, I don't see where it says stranded shielded wire in here. It just says 16.2. And 16.2 Romex is a whole lot cheaper than stranded shielded. So many times there's not much you can say to that, because we're only as good as what the manual says. But we've been around long enough to see what happens. And yes, it will likely work for some time. You may not ever have an issue with it, but the more rage you use, and when you're pulling that Romex wire, the more bends you have in it, the more issues you can have.
Steve, I wanted to back up a second, a little bit.
Sorry.
A little earlier, you were saying that the indoor unit and the outdoor unit, they kind of talk and listen back and forth. Does that mean that whatever protocol that is being used, you'll be sending voltage from the indoor unit to the outdoor unit and vice versa? Can you read voltage both directions?
You really can't read voltage both directions. What it's doing, yes, it will send a voltage signal, but it'll be going too fast for a meter to pick it up, and it will be less than what you're actually going to read. So the pulse is so I can't recall.
Let me rephrase that. Let's say you disconnect the wire outside and you're reading the voltage. Are you going to see voltage being sent from the indoor unit to the outdoor unit, and vice versa? Like, let's say you disconnect the wire on the inside.
Oh, I see what you're saying. So typically there's a starting place for that signal, and usually the starting place is the outdoor unit. For the most part, that signal derives from the outdoor unit, and it's carried out throughout essentially the communication bus of the system. So if you were to remove the two communication cables off of an indoor unit, let's say, for example, this air handler, it will not communicate with it at all. Now, if I just remove, let's say I cut those lines, the outdoor unit there will be voltage there. And depending on what sort of equipment it is, if it's started up before, if it's never started and it doesn't ever see that air handler, you may never have a fault. But if that communication's cut and lost, and that outdoor unit says, hey, there's supposed to be something here and there's not, you will get a fault on that. But it depends kind of on the brand of equipment. But that signal, if I were to put that same wire on just the indoor unit and remove it from the outdoor unit, you will not, unless it's a complete circuit, you will not, like a daisy chain, you likely will not see the carrying signal. That carrying signal comes from the outdoor unit power source. And when I say carrying signal, I mean the communication voltage bus. So, like I was saying earlier, Hisense is 5 volts DC, Daikin 16, Mitsubishi's 29. That's the signal that really pushes it along. And then the pulses are a fraction of that. They're not actually 29 volts. It'll be a micro pulse of, 2.8 on Hisense. It might be around 5 or so on Daikin. Yeah, plus or minus 5 volts. So each of these are basically binary codes, ones and zeros. That's what we're looking at here.
So there is like a starting point. Is that what you're saying? The COM bus is like
correct.
Is like the starting point. It's not like all of them are all starting. There is typically a central.
So, for example, on Hitachi and Hisense equipment, and it might be the same for others. I don't know about others. There is the home bus communication protocol will need what's called a terminal end resistance of 75 ohms for that communication bus. That is set at the outdoor unit, and it's only set at once. So let's say you've got 5 systems. You only need to set it once for all 5. If you have 2 of them turned on and they're all connected, that's going to be too much resistance. If you don't have any of them turned on, of these resistors turned on, this is just a setting of a dip switch, you'll have too little resistance. So there will be COM faults if it's too less or too much. It has to be kind of right within its range, and they're all defined. And what's fascinating is all these communication protocols usually work between 5 to 30 volts DC, and then it's up to that manufacturer on how they want it to communicate. So like HomeBus, which is a communication protocol, is up to, I believe, 32 volts DC, but we operate it at 5 volts DC, and that has, and with that signal, that has a lot to do with the resistance, that 75 ohm resistor, and the carrying signal. So there's all these kind of go into it's kind of what I was talking about earlier. It's all these small puzzle pieces form the bigger picture. But essentially, when we're talking a communication device, everything has to be connected. Everything has to have an address, and essentially everything's talking to each other, and we're all speaking the same language. Is kind of what's happening.
Can we zoom back out and just talk about? You mentioned earlier, like I wanted to touch on installation practices. Is there anything besides like the stranded wire that you would consider like a best practice?
I would never recommend junctions. This communication wire comes in boxes, and it's not. I've never seen a run where a box you couldn't go from point 1 to point 2 with it. So you want to really reduce any sort of junctions. And so you want to have a straight line from unit to unit, and you only want to ground the shield. You'll need to ground. They'll need to be shielded, and the shield is for really interference, noise. You really want to make sure you're setting it up for success, essentially. So,
what's noise? What is interference? Like what?
Interference would be something that would really interrupt the communication signal, basically the pulses. So those can be interrupted so easily. So interference, such as, let's say you're running the communication wire in a conduit with high voltage, that can cause a lot of interference. If you're running it, let's say you've got a warehouse full of radar detectors, unlikely, but that could cause interference. It's not like you're going to get it from that, but the one that you will get it from is high voltage, especially if it's 460 volt or our friends up north, 575. If you're running in a conduit with that, you can pick up a lot more interference. I've noticed that quite a bit over the years. 208, 230 isn't as much, but still it will cause interference. So you want to have a dedicated conduit for your communication, or really running it with the refrigerant line typically is the best way to go. You're not having a problem with that as long as it's a weatherproof jacket. You want to have. Oh, go ahead.
So the shield kind of just picks up all that extra
garbled
up language and just shunts it to ground, essentially.
Well, it basically filters it all out. It blocks it from interfering with our pulses.
And you mentioned grounding the shield, but like, all right, so I've heard people, you want to ground the one side. What will happen if you ground both sides?
I was actually about ready to get into that. So if you ground both sides, you effectively create an antenna, and that will be a pretty big interference to do that. So there's nothing worse than you doing everything right, and then you ground both sides of your communication wire, and you create some really big interference. And if you really which this is the thing that is really tricky, but the manuals, they usually do a really good job illustrating where to ground it. And it's always from one unit. You ground, let's say you're connecting an outdoor unit to one indoor unit. You're only going to ground that strand of wire once. And then the next one, from that one indoor unit to the next one, you're going to ground that once, and so on and so forth. If you keep grounding that same leg, you like I said, you've made a massive antenna, and you're going to get a lot of interference through that. And it's hard to really explain that to some people that don't really understand what's happening. And
Can I try? So let me step in here because I have a real world situation. Somebody brought it up here. I have this actual issue in my house, and so this is one of these things where people always imagine that me or people like me, when you install stuff in your own house, is like, that's probably the best air conditioner ever, right? It's like, no, absolutely not. Because by the time I get to my own house, I absolutely despise air conditioning, and I do it the worst, sloppiest way I can possibly do it. So when I installed this Carrier Infinity system in my house, I didn't run shielded cable. And every time, and I think there might be a grounding issue in my house, some sort of weird thing. And we're also in Florida. Our water table's really high here where I'm at, like my whole yard floods. So anytime we get a near ground strike from lightning, which happens all the time, lightning capital of the world, my Infinity system just faults out. It just goes into communication loss. And I have to do like a very specific, I won't go into it, but like a very specific sequence of things to get it to work again. And what we ended up doing, and it still isn't, because I think I'm going to have to, the problem got a little better, but it's not completely solved, is we took the additional leftover conductors, we put them all together, and we grounded them on one end. If you imagine, so what happens in the case of a near ground strike is you get basically this pulse of high frequency electricity, right? High frequency current. And it interferes with everything. So it creates all this EMF, all this electromotive force, all this magnetism, which is then induced into this conductor. And so by taking these additional conductors, putting them together and grounding them on one end, basically you're shunting it to ground. If I were to do it on both ends, all that I'm doing now is creating a ground loop path. Like I'm actually making a path now for it to more easily induce into the other conductors in the bundle. And a shield just does the same thing, just better, right? So a shield, rather than just having some wires running around the conductors I'm using, it's actually wrapped all around. It's a metal, coating, and you take it and you kind of twist it together and you ground it on one end. If you ground it on both ends and you get something like a near ground strike, like we're talking about, you're going to have all this current. Actually, it could potentially following that path, because it's going to follow every path there is all over the place when you have this massive, massive surge, and that's just going to make that problem worse. So that's one example, but there are many others. Obviously, like you mentioned, running next to high voltage conductors is one. Other types of high frequency equipment in the home could potentially do it. Somebody has an MRI machine in their house just for fun. Who knows? You never know what people do nowadays. People are into some weird stuff.
Crazy hobbies.
Yeah, absolutely. So that's one thing. Another couple questions while I have interrupted the flow of the conversation. Quickly, somebody asked about transducers early on. Like, so what's a transducer again? We sometimes take that for granted. But talk about quickly thermistors, temperature sensors, transducers, and the role that plays in communicating equipment.
So transducer is different than they're both. I guess let me back up a little bit. All the unitary equipment will have a pressure switch of sorts, and typically it'll be a high pressure. Some of the more complex unitary equipment might have a low pressure switch, but those are really just fixed switches. When a pressure gets to X amount, they either open or close, whatever they are. A transducer is a communicating device that it reads what the pressure is, and it has a DC voltage feedback. So whatever I don't have any data in front of me right now, so I'm gonna make some stuff up for the sake of explaining it, but let's say a pressure transducer will have a scale, just like a thermistor would when it reads temperature. It looks at resistance. Transducer looks at DC voltage. And so typically they're about 5 volts DC, and it has a scale. So it'll send 5 volts to it, and it'll send back X amount. Whatever amount comes back is the voltage, is the pressure of the system. So let's say it's 100 PSI is 2.4 volts DC, whatever. If it sees 2.4 volts DC, it sees, okay, we're at 100 PSI. And so those are all components, and these are all communicating bits as well. So these, if you're communicating out, like an outdoor unit wants to see what the head pressure is before it runs the compressor faster, it looks at this, it sees what these are doing, and it all kind of talks to the main control board at the outdoor unit and says, I need to run faster. What do I need to do to run faster? And the outdoor unit control board will say, you need to look at your, depending on the model, depending on the brand, you need to look at your discharge pressure. You need to look at discharge superheat. You need to look at your target condensing temperature, target evaporating, whatever mode you're in, cooling or heating, and look at all these functions, all these parameters. If these all check well, and it proves that we need to spin faster or go slower depending on which direction we're going, then we'll go that direction. So let's say the example I always say in VRF is, let's say you got a building that's 70 degree set point throughout the entire building. And all of a sudden, someone wants to open a window. It's really cold outside. It's like Florida. It's freezing here for some reason. And so the window's open. Now we're bringing in a lot of really cold air. So that cold air is going to get to that indoor unit. We're talking VRF here. That cold air will go to that indoor unit and it will bring down the condensing temperature of that indoor unit. And so our head pressure will fall just slightly. And that will go to our outdoor unit. And our outdoor unit will see our target condensing temperature just lowered. We're not exactly sure why, but something lowered it. It's you can figure out why. You can look at some of the things at the indoor units, but that's kind of irrelevant. That's just noise at that point. It just sees I need to spin faster. My pressure is lower. My target condensing temperature is dropped. So we need to increase it. What do we need to do? And it's going to look at some parameters, and it's going to run faster to bring that pressure up. And by doing so, it talks to all these components. It talks to the thermistors, which the thermistor is essentially just and a lot of, I think with communicating systems, we're not really ever in that 10K thermistor land. I wouldn't ever really say that any of these are really universal anymore. We're kind of out of those days. I think those days have pretty much moved on for the most part. But in a communicating system, a thermistor, it'll look at the temperature, and based off whatever resistance that is, will tell you what the temperature is, just like like a transducer. So it'll look at all these values, all these metrics within the system, and it'll tell it to speed up, speed down, go faster, turn off, all these different things.
So simplified, transducers, pressure.
Yep.
What's the pressure? Thermistors and thermocouples, temperature. One of the things that somebody posted here, I wanted to put this up here quickly because I wanted to address it. Oh no, I can't find it, but it was basically saying he's never seen a case where shielded cable would ever solve a problem. And one of the things that I want to be really clear about is that the shorter the distance that this stuff is run. So if you're primarily working with communicating systems and you've got a basement and the condenser sitting right outside and you've got a residential application, it's going to be unlikely that hardly anything's going to matter. But when you start talking about VRV, you have much longer cabling, much more opportunity for issues. All of this becomes more important. But another example that I wanted to give, and I think this is coming, because we're talking about communicating systems here. There's all different types of communicating systems. In the grocery store world, we use case controllers and all this, and more we're going to Cat5. And you want to talk about finicky, like you bend it too much, and all of a sudden you start going into comm loss. This stuff is super, super finicky. So things like, making sure that and again, shielding is, in the case of Cat5, shielding is rarely a problem because they use twisted pairs, and they can do that because it's much smaller size wire. So when you have twisted pairs within Cat5, that sort of offsets a lot of those challenges that you get with interference. But it's all the same animal, right? If you have issues with running it alongside high voltage or even bundling it too much, where you're looping it too many times, you'll run into issues. There's all kinds of things that begin to matter more and more. The longer that it is, and also depending on the protocol, you'll get some manufacturers who will say use shielded. You'll get some who say you don't have to. But that doesn't change the fact that if you're running into a problem, again, my house, carrier doesn't say that you need to use shielded cable. But in my particular case, and again, I think there's probably a grounding problem in my house, like I mentioned, and I won't go into that. Again, I built my own house, so it's all my
who did
fault.
the electrical work?
Exactly, I did that too. But again, hey, I did it with like my 11 and 12 and 13-year-old son at the time. Okay, so give me a break.
So it was a good bonding experience.
Yeah, another thing he said, it was the same guy. He said he put this down, surge protection. Surge protection isn't going to do anything for a near ground strike. That's going to protect some things, but it's not going to address the type of issue that we have where it's traveling everywhere. Surge protection is basically just taking the high voltage distribution. And then here's what he said: I've honestly never had an issue where shielded wire would have been a solution. LOL. And again, we've installed countless ductless systems with solid wire before we knew any better. And we didn't have issues with that. But again, the ones we're installing are on lanais where it's like condenser here, ductless head, 10 feet away.
Right.
It's very unlikely that you have two connections. It's not that big of a deal. But the longer it gets, and the more that you're pulling it through difficult situations, the more likely you're going to stress it, and you're going to get those microfractures, like Steve mentioned. Sorry, I had a lot to say there, but I just wanted to get
it's
all
good.
that out.
No, and you're right. And when you look at some of these, and these all really stem back to the manual. I've seen some people ask about, the size of wire, which the size of wire definitely matters. And you really want to stick with whatever the manual says. It varies from brand to brand. But if you ever, find yourself bored and you want to go through technical service manual or installation manual, which I'm sure that's all what we do for our free time. You get to the communication wiring section and look at some of the limitations. That's a perfect example of just because you can doesn't mean you should. For example, on our equipment, on Hisense, the remote controller is it's communicating, but it's a different signal than the communication bus. So those connect directly to the Ender unit. And same thing with Daikin, same thing with Mitsubishi. Mitsubishi does have a communicating controller that's on the communication bus. So that one is a little different. But the ones that connect directly to the Ender unit, most brands, you can put those up to 500 meters away from the Ender unit of cable length. And you think about, that's kind of staggering. And you never really want to get near those limits. Those are maximums, and you really want to be as really far away from those as possible. But it's always really interesting when you go through those manuals, you kind of read through the fine print and really see the limitations on communication, what can be done. If you look really closely with a magnifying glass on most of them, you'll see exactly where they have you ground the wire on Ender units, which it's not the easiest thing to see, but usually it's there. And it's easily missed. It's very easily missed. And so, in fact, I would suggest anyone installing a communicating system or that uses a two-wire DC communicating protocol like what we're talking about, pay real close attention to the page, the diagram page of the manual that shows the wiring. Look really close at the outer unit, the terminal blocks, and you'll see where it shows a ground. And you'll see where only one leg of that communication wire is grounded. It's not grounded in every single spot. So pay close attention to that. It's there. It's not the easiest to read, but it's certainly there. And it's kind of, the more you dig through this stuff, that's the thing I've always never cared about manuals. You'll find the most enlightening information in the most unlikely spots.
It just seems like one of those things that if you know that there's the best way to do it, you might as well just do it, because you don't ever want to have to go back and try to fix it.
Exactly. I always, with our equipment, you can use 20 gauge on our controllers. I'm telling everyone, I'm training everyone, use our communication bus requires 18 gauge on Hisense equipment. So I'm telling everyone, use 18 gauge, even for the controllers. It'll fit on the controllers, so you don't have to struggle with it being too big. You only have one box of wire. You don't have to run the risk of pulling 20 gauge accidentally from one Ender into another. I mean, it just make it easier, reduce as much liability off yourself as possible. Once you you really figure out one system, it's really not difficult to really nail down the other brands. They all have kind of different intricacies, but they all operate very similar. It kind of goes back to the protocol. You have Modbus, you have Home Bus, you have Connects. All these are very similar, but they're all their own different language. It's think of it's English, it's Spanish, it's Chinese. It's they're all speaking that language within that system, and they communicate effectively. So that's why everything needs to see everything. Everything needs to talk to everything.
Saying it as a language is actually very apropos, because if you think of, like, we all use our vocal cords to create vibrations through the air that are then received by our ears. Like, it literally is transmitter, receiver, waves.
Exactly.
And so we can say, hey, they're all the same in that regard. Every language is, transmitter, receiver, waves. In the case of how you actually interpret it, though, if you don't know how to speak Chinese, it's not going to mean anything to you. And that's the challenge in these sorts of classes or these sorts of live streams. People can be like, well, yeah, but how do I measure it? It's like, well, you'd have to know how to speak the language, and you'd have to have an oscilloscope, which you don't have either, really.
The oscilloscope thing is interesting. It's like it's neat to see it, but at the same time, you don't really need to dive that deep into it. Typically, if you have a communication fault, so let's say, and your communication faults will be one. Let's say the most basic. Let's say they ran solid core wire, and you're not communicating. So let's say you're telling it to run fan, and it's not running, and that could be, you may not be getting a fault code. You may not be a comm issue, because those pulses are getting lost. And so it's not like it's not receiving the injury. It's not getting a signal loss. It's just, or I'm sorry, a conflicting signal. It's just losing it. So it doesn't know what to think of it. So it just doesn't really do anything. So when you come across communication systems where it's not doing anything, and you've replaced boards, you've done all this, really, it's amazing how many times I did this when I was at my time at Mitsubishi. You come across these systems that are pulled in solid core wire, and it ran for years, and now all of a sudden it doesn't. And that was the final thing: replace the wire. I know it sounds difficult. I know it's a lot of work, but I guarantee you that will likely fix your communication issue if you don't have a fault code. If you do have a fault code, that makes it easy, because the communicating systems, the great thing about them is everything's addressed, so they'll tell you where the fault's at. So let's say you have a daisy chain system, and let's say I've got a communication fault on indoor unit number 5, and I cannot see number 6, 7, and 8, 9, and 10. I've got 10 indoor units, so I only see 5. That really gives you a good indication where to look. There's a comm break there. I didn't put my wires aren't landed. Something, mouse chewed up the wires. There's something going on at indoor unit 5 that's making me not see the rest of the indoor units. So in a daisy chain system, it's very easy to see where a comm fault could be. And so it's one of those things. It's neat to have an oscilloscope to really see that stuff, but at the end of the day, for the sake of troubleshooting and getting equipment back online, it's not required. It's really just kind of, using common sense and thinking, okay, this is trying to talk to it. It can't. What do we need to do? If we have a fault code, that's easy. We can go off that.
Yeah, Steve, could you? So you were talking about just kind of how sometimes we really want to know like exactly how everything's working, but like sometimes we just can't, especially as we get into more and more communicating systems, and we're not going to be able to understand all these languages. Can you give us, just give us a sense of how we can work on stuff that we don't feel like maybe we're going to know everything about?
We're never going to know anything. That's why Bryan made this live stream. That's why Bryan put together HVAC school. It's impossible. And to think you have to know everything about whatever that system is before you go into it. It's the same mentality of, I'm sure if any of you guys I know Bryan's dad. One of those, when you hear people say, we're going to wait till we're ready to have kids, you're never going to be ready. If you're going to wait to that point, you just as well just hang up your gauges and not do service work, because it takes us getting in there, getting our hands dirty, and figuring it out. And really, the best part is to take notes. We can get manuals all day long. We can download them all day long, but put pen to paper, take notes. It's harder to forget notes than it is a book that you downloaded or that's tossed in the back of your service van. But they're all different from, as far as the communication, the voltages, they're different from brand to brand. So even guys that work on one brand, I've had the luxury of working only really on 2 brands for the past 7 years. And that's kind of lucky for doing that. But it's kind of skewed my view of my current, the brand I work with now, because I've been drinking from the Red Cup for so long that I have a hard time understanding how things work outside of the Red Cup. So there's kind of pros and cons with it, but the best way is to, a lot of these manufacturers do have free training. They do have free resources. You might have to sign up for it. You might have to register for it, but the information's out there. There's a lot of really good resources, but to think that you have to know how everything works before you can understand or really work on it, you'll never get there. And that's where you just need to kind of dive in and keep it simple. Start with the basics, power, troubleshoot, fault codes, and kind of go down from there. The same skills that you learned on a 13 SEER Goodman AC a couple of years ago are the same skills that's going to work you through a VRF system. Same troubleshooting skills. And one thing I've always told guys when I'm training classes is VRF is very, and especially communicating systems, they're a lot more complex and a lot more complicated than a standard 24-volt AC control system. And so when something fails, a lot of guys will think it's a complex system, so it's going to be a complex issue. And you'd be surprised how easy most of these fixes are. And that's kind of the mentality that we need to. I try my best when I do the training with the guys around the country is, shake the thought that, when you work on this equipment, you kind of put these blinders on that you're looking for really complex stuff, but chances are, especially communicating, it'll be pretty simple. It's usually down to wiring and addressing. Those are usually your two issues. If it's addressing, it's pretty simple. You'll usually have a fault code with that, and it'll tell you exactly where you messed up. That's the beauty of it. If it's wiring, you might have to chase it for a little bit. You might have to double check voltage, but if you tried everything, you've checked voltage, you've checked resistance throughout the system, you might just have to pull new wire. But it's worked in several situations I've been on, but you don't just want to start throwing stuff at it. You really need to use your troubleshooting skills and dive through the system. Make sure you're doing the right steps. Don't just, load parts in the parts cannon and launch it.
No loading the parts cannon. A couple things that I want to mention here quickly. Visual inspection is huge, like we mentioned. Massive. Like, just look for obvious things. Tug on wires. Make sure they don't come loose. We're talking about so many different things here that it's kind of tricky. A lot of this is VRF, residential. I keep bringing refrigeration into it because that's just where my head is right now. But there are some like universal things here. And a lot of it is, hey, make sure you have really good connections. Hey, make sure that the wires are landed on the correct terminals. You mentioned addressing, which I want to ask about. But this question came up about crimp connectors. And again, I think it's important to recognize you may be allowed to do crimp connectors in a lot of cases, but are crimp connectors the best connection? And the answer is soldered connections are the best, right? I mean, if you have to make a connection, proper solder connections are the best way. Is that practical in a lot of cases? Probably not. Can you get away with it in some cases? But do you have any thoughts on crimp connections specifically, Steve?
No, because that's usually what I did in the field. I was very OCD when I did my communication wire. Even when I did my I don't know if you saw my new ridiculous system I have in my house, but I was very, very OCD with how I ran the communication wire. Everything had to have the proper, what do you call it? I guess the C or the U-shaped crimp connector on it. I didn't want the wires going straight into terminal block. I didn't want them to be the terminal block kind of off one side because it's screwed down wonky. Crimp connectors work well. I haven't seen it where they don't. You're right. Solder is the best, that you're going to have the best connection. But I never had a solder gun in the field, really. I mean, I had one back in my house on my workbench, but I never really brought it in the field. In fact, I use it more now working for a manufacturer, which is kind of counterintuitive, than I ever did before. But just as long as the crimp connections are at the terminal block, they're not like in the middle of the run. We really want to avoid junctions and wire connections, wire nuts, crimp connections in the communication line, because if you do that, you're going to run the risk of having a communication loss. You can lose with the resistance, with voltage loss. You could really lose communication through that connection, and you're really you're rolling the dice there. I mean, if you have the wire, do it. Don't run the risk, because you guarantee that will cause a callback.
One of the things I want to mention is when people make crimp connections, though, there's a lot of people who don't do them right. And so like that's the thing that worries me, is that there's a lot of people using the wrong type of crimp for insulated versus uninsulated nowadays. They're labeled differently. The ones we have nowadays are actually those ratchet crimpers that actually have the color like right on it. And those are the ones I give all my techs, and that makes it a lot less likely that people are going to mess it up. But that's the thing. It is something that, like, if you're a professional and you know for sure what you're doing, then absolutely it's going to be fine. I mean, we've done it for the longest time. One of the things that I wanted to kind of bring up quickly, because you've mentioned addressing a lot of times. And of course, in the residential world, that's not really something we generally are messing with. What do you mean by addressing?
So in a DC communicating system, the ones we've been talking about, they will be addressed. Now, some of the communicating systems, like the one-to-one unitary, they still will be addressed, but they'll be addressed from the factory. So it's really typically not a field setting you have to do. But in a larger system, like a VRF system, for example, most brands have auto addressing, which works well enough. But you do run the risk of, if you ever lose power for an extended period of time, the addressing could be deleted and it could be reset to different numbers, which isn't really the biggest issue. But if you do have them organized by address number on a central controller, that can kind of throw things off. Our equipment, Hisense, Mitsubishi, Daikin, most brands can all address by themselves. So you just turn the power on and they'll take off. Whenever you start bringing equipment into a centrally controlled system, so let's say you have, if it's just a standalone system, one system, it doesn't matter if it's got 1, 2, or 3 out units twinned or tripled together. That's really just one system. And you can, if that's all you have, auto addressing is fine. You really won't have an issue with it. But as soon as you bring it to a centralized control where there's more than one system, you've got 2, 3, 4, 5 complete separate systems on a site, that's where you really actually want to go into the equipment and do a hardware set. Auto addressing is a software set, and it can be deleted by loss of power for an extended period of time. When you're setting a hardware set, most brands will use either rotary dials, will use a dip switch, or some, like Hisense uses a binary code, an 8421 binary code for 0 to 63 addressing. So every piece of equipment has to have an address. And so, for example, on most 3-pipe systems, you'll have a system number, and then you'll have an end-to-unit address. So the best way to think of it is, think of the system number as the street name, and then the address is the house number. So all those houses are on that same street. They're all talking to that one out unit, that one system. And those need to have the same system so they all know who they're talking to. And this is where it's really crucial when you have a large VRF system, when you have addressing. If you have addressing issues, this could be part of your communication issue. Is, you've got 2 address 3s. Well, whenever you turn that on, you'll always get a fault code right away, because as soon as it turns on, it's communicating. It'll turn on and it'll say hi. And when it does that, it'll go to 3 and it'll see 3 and it'll say hi, and 3 will show up again and say hi again. And it immediately confuses the out unit and says, we can't have this. These are the same. So we need to make sure everything's addressed separately so that everything can talk at the same time. And it's also really interesting if you look at, when you kind of dive deeper into VRF service work, when you look at like inverter boards, for example, you might have inverter boards for the compressor or the fan for outdoor units. You'll notice a lot of those will have dip switch banks on them, and those will be addressed too, because those are communicating with the main board. And so if you ever replace an inverter board on a piece of equipment that has 2 fans or 2 compressors, and you line up the dip switches just like the one below it or the one that you're not replacing, you will get a communication fault. It'll be different than the ones you normally get from an indoor unit, because this isn't an outdoor unit cannot see the indoor unit. This is the outdoor unit cannot see the outdoor unit sort of communication. And so everything kind of has to talk to everything. And so for it to talk, it has to have its own name, kind of like all of us. We all have names in the bottom left corner of our screen. If I was Bryan Orr and Bryan Orr was also Bryan Orr, this would get kind of confusing. And so it's all about, everything needs a name, everything has a place, and everything communicates within its place. A lot of, I'd say, address errors happen during service work when the dip switches aren't set properly. That's usually where you see them the most. Startup and then service work.
It reminds me of a dream that I had when I was a little kid. That I was standing in the living room and I looked in the kitchen and my mom was there, and then I turned around and my mom was also there, and it was really scary. It's just like that. Like, you don't want to have more
Television.
than one mom. You know, like, you only have one. It could be your dad, but, you know, you got to address it right. It's very, very important.
Double vision, not good.
It is. It's just not. It's
Yeah,
really
I
scary.
believe that is a glitch in the matrix when you see that.
I know. I should have kept that dream to myself. We're going to stop that now. So I really like this question from Chris Hughes because I think it addresses a lot of what we're seeing occur. And he says, how long till we see VRV, VRF move into the grocery store scene for low temp grocery refrigeration thing? Again, it's a grocery question, so that's why I like it. But like grocery refrigeration was like the original VRV, VRF,
sure.
And everything is actually becoming more similar. Not necessarily in the language that they're speaking, or even in the types of wires that they're requiring and all that. But in terms of the way that things are all going to communicating, we're seeing it in residential, you're seeing it in grocery, you're seeing it in VRF, VRV, you're seeing it in other types of, chillers and everything else that we work on in our trade. So understanding the basics of how it works, the sensors, addressing controllers versus thermostats, all that stuff is actually going to be critical for everything we do in the trade. And really, you're actually seeing more things become similar than they're becoming different, honestly.
I would agree. As you know, AHR is coming up, and it's always interesting to walk the aisles at AHR, and you see some of the really wild stuff some of these manufacturers are coming up with, and it's, I don't know if it'll be too far off. And you're right. You know, refrigerant guys, rat guys, those make the best VRF guys. They have the best understanding of refrigerant flow of anyone out there. So that is the original VRF. As far as how it communicates and how everything goes, yeah, I don't think it'd be too terribly long, especially when you consider how heavy the push for when you look at like the IRA bill, the Inflation Reduction Act, how heavy that was for the HVAC industry, the rebates, the incentives being given just for that, and it's not just for consumers; it's also for manufacturers. There's an enormous part of that bill that is geared for manufacturers to set up shop in the United States to build manufacturing facilities here, to produce more that can really keep up with the demand for the market. So I know there's a lot of guys in these Facebook groups that think the best way is a 13-seater Goodman with a 80% cast iron gas furnace, but that's not. I mean, unless you live in the mountains and you're off by yourself, completely off the grid, that's not something that's going to happen. I mean, communicating equipment isn't going to go away, and with how convenient things are, I mean, the ability to tie it into the Internet of Things, IoT, all that stuff, what it can do. Yeah, it's more things that can break. I know someone's probably going to comment that here probably pretty soon, but it's interesting of what we can do with it. Yes, you can still get basic equipment if you still want basic stuff, but I think with the advances and the pushes with the industry, especially from really government, with the rebates and incentives, I don't think there's going to be any let up anytime soon. And I'm pretty sure we'll see equipment like the VRV, VRF equipment for refrigeration, grocery store. The only thing is all that stuff is very comfort driven. So they've got a laser focus on comfort over in Japan and China where the stuff is produced. And so getting them to let off the gas on that would be a little different. So it'll likely be a different manufacturer or a different industry altogether that really pulls up, kickstarts that.
You mentioned, there's more parts to fail. It's more complex, right? So I know we got to kind of wrap this up, but what about, what's the reliability on these compared to a basic 13-SEER system? If you had two awesome installers installing a 13-SEER next to a VRF or just a 20-SEER train, whatever it is, and they both did their job perfectly, which one would you expect to have more issues service-wise?
That's a hard comparison. That's like saying if I get a 1950 Ford truck and a truck from now, do I think my power windows are ever going to fail in my 1950 Ford truck? It's hard to really compare that because there's a lot more that can go wrong. It doesn't mean It certainly it will. It's just there's more parts, there's more things that are in the system. So to that point, a 13 series system, a very basic system, has less parts to go wrong. But as far as reliability, it's hard to say. If everything's perfectly installed, everything's done right. You got the trim charge is done right. The piping is measured properly, wired right, and it's applied properly. I really don't see an issue with reliability. There's a site when I was at Mitsubishi. There was a site in Oklahoma City. It was a high rise. It was G generation VRF equipment, and it was one of my favorite VRF installations I've ever seen. The building at this point is probably about 22 years old. When people say VRF is new equipment, it's been around for quite some time. I've got the letter from 1993 when the first heat recovery system was installed in the United States. But this building in Oklahoma City has been a absolute rock star for VRF. It's been like this was one of the examples why I really got into this industry and really liked it so much. Was really this site. The only thing they've had to replace in the 20-some years that this equipment's going are condensate pumps and some controller wire that was on the roof that got bleached by the sun. There's been absolutely no issues with this machinery. It was a perfect install. It's piped right. And it all goes down to how it's installed. If everything's done right, which I know that's a big ask, if everything's done right, everything will work right. But we live in the real world. So it's a hard comparison because you got something that's really complex and something that's not complex. And so you're kind of measuring two different aspects of it. But as far as reliability, it's really hard to. I would say they're very close. I mean, there's more things to it, but so long as everything's done right, this stuff wasn't designed to fail. I've been to the factories. They're not in their high towers and like Mr. Burns, wanting Americans just to have failing equipment all the time. They want this stuff to work, and it's amazing when it works, and when it really works, it's pretty impressive. I'm still dazzled with my ridiculous system at my house. It's complete overkill, but
I actually one of the comments is compare Mercedes to Toyota. That's one of the comments, and I think the example is Mercedes is so complicated and Toyota is simple, but Toyota ain't simple anymore. I mean, like these are not simple cars. They're designed with reliability at the forefront. Versus luxury, and that's a choice that different manufacturers make. And so you can't say that all these pieces of equipment are the same. They're not going to be. Some will be very reliable, like a Toyota, and still be very complicated in a lot of ways, and some won't be as reliable. And that's only left to see. But again, from our standpoint as contractors, installation, commissioning, and maintenance. Whenever we do this, we have to think about those three things. And if we do those three things right, most pieces of equipment will be reliable. We'll have outliers. We'll have our equivalents of the leaking evaporator coils that we see so often that like we pull our hair out and we know we didn't cause. Capacitor failure. You're going to have those things that are going to occur that aren't our fault. But those are the three things we need to do. And if we do those three things with VRF, communicating residential, communicating commercial refrigeration, then you're going to have the best. Overall results. Again, for those of us who are fans of simplicity, there's something to be said for that, right? There's something to be said for a 57 Chevy. There's something to
absolutely.
that.
Sure.
But we don't have a choice, right? We don't get to decide. It's like so many of times when people talk about the EPA and all that. Hey, it makes good dinner conversation. We can talk about things we like or don't like about the industry, but we're not in a position to make those decisions. So for us, we have to install properly, read our TFM, read the fantastic manual, as I always say. We have to do things accordingly to those practices. We need to commission it properly, make sure that we're actually testing everything out, and then we need to maintain it properly. And if we do that, we're going to be in really good shape.
The install is the most important day of a heating air equipment. Getting that right will set the system up for success.
Absolutely. I said I wasn't going to talk much. This is the problem when I'm on these live streams. I end up yanking too much. But yeah, Steve, Matt, Adam, thank you guys so much. We're already well over, so I'm going to go ahead and end it here. Any final words from anybody? Steve, anything that's like your final like quote that you want to be known for all eternity?
No.
No.
I'd rather not be known.
Okay.
Good end.
Good
Yeah,
stuff. Rather just fade.
Yeah, I'd rather just
yeah.
slip into
Oblivion.
madness.
Yes.
Slowly slip into madness.
Yes. Ooh, yes. All right. Hey, thank you guys. I appreciate you. Thank you, everybody who watched. It means a lot. Thanks to Hisense for allowing you to do this, whether they know about it or not. They let
They
you.
do. They do.
Yeah. So it's all good stuff. I appreciate that, and to everybody who takes the time to learn in our industry and share it with whoever's riding in the truck with you, whoever you deal with in your company. That is where the real magic happens. So thank you for doing that, and we will see you all again at our next live stream.